I'm just going to tell you briefly about the other ladies that are sitting here, and we'll begin with Susan Avery, who is a PhD, and she's the president and director of the Woods Hole Oceanographic Institute. And I think I'm just going to let you read the rest of her bio in your programs, but I want to mention that I grew up on Cape Cod, so I have a very deep affection for Falmouth and Woods Hole. And when I was a little boy, I went to see Atlantis and Alvin. And I remember Alvin going into the ocean. It might have been with Jacques Cousteau, I'm not sure, but around that time. And so that led me to my early interest in studying marine biology at Cape Cod Community College. And then Aspen sort of took me into the mountains. So, Allison Loomis, dear friend, and Allison is a naturalist who recently came from a journey to Alaska and is going to tell us a little bit about what she's seen up there and give us sort of a fresh bird's eye view of the state of Southeast and some of the glaciers up there. So, but let's, you know, following on Dr. Earle's wonderful presentation, and I also want to let everybody know that we're very, very proud of the fact that Sylvia is a board member of the American Renewable Energy Institute. Thank you for your leadership and joining our organization. So before we get to the PowerPoint presentations, let's have just a little bit of a free-form dialogue in terms of, you know, where are we at? And maybe we can start that with the acidification issue.
Go for it.
Okay. Well, let's the acidification issue is certainly is a result of the increased carbon dioxide that we're putting in the atmosphere. Approximately 50% of that increased carbon dioxide remains in the atmosphere, and about 25% is uptake by plants and forests on our land, and about 25% is dissolved in the ocean. And when that carbon dioxide is dissolved in seawater, lots of chemical reactions occur. It actually is fairly simple chemistry when you think about it. It's not very complex chemistry. But the resulting issue is that the pH of the ocean declines, okay? And the consequences of that are immense to ecosystems that rely on bicarbonate for the production of food, of growing, for growing, and for basically their existence. And that primarily is the coral reef systems, as well as the shellfish that require that calcium to build shell. And you know, and a shellfish is fighting for energy that it's going to use to build shell, and energy that it's going to use to reproduce. And so that is the basic story of ocean acidification. Now, ocean acidification, that's only one part of the ocean acidification story, because there is naturally occurring ocean acidic natures, just the nutrient upwelling. You may have heard a lot about this in the oysters fisheries on the West Coast, that there is a natural cycle of upwelling of lower pH waters to the surface at times, which can kill off oysters and make it difficult for certainly aquaculture that is looking at shellfish. So in a nutshell, we're basically looking at a planet through human activities and an ocean that is warming, that is souring, and that is gasping, okay? And think about it. If you had a fever all the time, and your electrolytes were constantly off and your metabolism was not functioning very well, and you had to really labor to get oxygen, you probably wouldn't feel too good, okay? And in a sense, that is what the science is trying to understand, is these multiple stresses that are in the ocean and how that changing ocean is going to impact the conditions of the ocean in the future and its biological and healthy functioning. So I can stop there, but I can go on.
Thank you, Susan. No. Thank you, Susan, for your overview. And maybe Allison, you can give us just a couple of snippets of what you've seen recently.
Well, I studied this issue 10 years ago as a quaternary geologist. And at the time, they thought that the surface oceans could only absorb a certain amount of carbonic acid. But it turns out it absorbed a lot more than they initially imagined. So the impacts are happening pretty rapidly. I mean, it's something I saw in Alaska. Well, it's in California and British Columbia as well, but there is a melting sea star epidemic. We're losing all our sea stars really fast. And nobody really quite knows why yet, but we do know that they're very stressed from the warming waters and the acidifying waters. Yeah, in addition to the oysters and the scallops are having a lot of problems in British Columbia. So it's happening fast, way faster than we thought.
And as Sylvia has said, the average person might say, well, why does that matter to me?
Well, because we're all reliant on the basic systems that are governed by the ocean. The planetary chemistry is driven by the ocean. When you disrupt the carbon cycle, the nitrogen cycle, whatever it is, everything rocks. And the acidification, again, you've changed the chemistry. It's not just the obvious things. I think the thing I worry about most are the effects on the little guys, the small plants.
Small plants.
Some of them require or have as their basic structure a calcium carbonate shell. Another word to remember, coccolithophorids. Prochlorococcus, coccolithophorids, go for it. Impress your kids. But they're beautiful, tiny creatures that are really vulnerable to changes in acidification. I mean, becoming more acid. And another small group of animals that are very widespread, they feed on the phytoplankton, and like the small fish and like the squid, they're middlemen, pteropods. They're swimming snails, and they're extremely abundant in Antarctic waters and actually throughout the ocean as a whole. They're a common form of zooplankton. And they have this, as swimming snails, they have a basic calcium carbonate shell. It's vital to their existence. And there's evidence in Antarctica in particular that is already having an impact on the nature of their internal shell. So, why should you care? Because it links right back to a planet that works in our favor. I keep thinking about astronauts. They know they have to take care of their life support system. That if their life support system fails, they're done. If our life support system fails, we're done. Our highest priority has to be look out first for breathing, for water, the water cycle, the carbon cycle. I mean, maybe you hadn't thought about it before, but it's time to understand these things and get your kids up to speed, because we need to make this an intergenerational thing. This is not going to stop on our watch. We are leaving a planet that is not the same. I tell people I come from a different planet because the planet I came from is different from the one we've got today. And we want to try to edge it back toward a more stable system going forward. We can't go back, but we can make it better than it is.
Mm-hmm. Yeah, go ahead.
Well, I just want to follow up on that. In terms of ocean acidification impacting krill and other small critters, whales are dependent on that. And right now we're looking at the humpback whale and maybe others being taken off the endangered species list, but we haven't done the proper studies of what happens when they lose these animals or they drift off in different currents. And so we need to consider things like this. It needs
Absolutely.
to be integrated into management
future.
plans.
Please.
So let me add another dimension of where and why why scientific research is so important in the ocean and the interconnectedness that science can bring to this question. And with this ocean acidification problem going on, there's a real concern about identifying parts of these special ecosystems that might be more resilient to a rapidly changing ocean and hence have more capacity to perhaps evolve so that we maintain some of that. And identifying those and their biological functioning and figuring out how to protect them in ways that will continue to have sort of a seed, if you will, that will allow us to continue to make sure that this changing ocean has some of that capacity remaining is one of the things. We have a scientist who's working with Palau government and the Nature Conservancy in developing the sciences. And in a very large marine protected area that Palau has in the middle of the Pacific, they have found a particular coral reef ecosystem that does appear to be a little bit more resilient. And now they are taking action to put a lot of resources in understanding and protecting that for our future.
That's fantastic. And
Hope spots.
hope spots, and I want to get to that. And I know that we have a couple of PowerPoints, but before we go there, let's talk quickly about these hope spots, because it's my understanding that 2 out of every 3 breaths we breathe come from the ocean. Most people think that, you know, the trees supplies the oxygen, and they do, but it's
More
really
than half comes from the ocean.
more than half. And so, in terms of the cycles of photosynthesis and respiration and transpiration, and why we evolve as our own creatures and mammals and so forth, to get to the hope spot piece of that equation, and that your work, Sylvia, through Mission Blue, and how we've been able to put the focus on some of the governments and how urgent it is to preserve these areas. Can you just give us a quick update on how that's going?
Early in the 20th century, Theodore Roosevelt was a leader in the concept of protecting areas on the land that, if they hadn't been embraced at the time, they'd be gone. But the idea that others could see that they were vulnerable to being chopped up, mowed down, or turned to what people thought of as more useful purposes. But by embracing big tracts of the land, watersheds, forests, areas that were important for wildlife, birds, whatever, were banked, if you will. And it's been a steady process. We've sort of sloped off on that on the land. We need to amp up more. Individual organizations such as the Nature Conservancy and Conservation Fund and others have sort of picked up the slack where our government has stepped back from that process a bit. But it wasn't until the late 1970s that something similar began for the ocean with the National Marine Sanctuary Program. And, you know, the sanctuaries are a step in the right direction, but they're more like national forests. They're managed areas. National forests, you cut the trees, you have a management protocol, but marine sanctuaries, you cut the fish, you take the squid, you still extract, you manage it, but it isn't like having a fully protected area. And what you mentioned, Susan, about what Palau, the government there, has done is to look at their 200-mile exclusive economic zone, little bit of land, big blue backyard, and they've said, it's more important to keep this area intact, our blue assets, than to open it up, as they have in the past, to industrial fishing, sharks, tunas, and the rest, because they've seen the consequences of extraction and the impact on the natural systems that, turns out, are more valuable to them than selling off piecemeal the wildlife that doesn't just instantly come back. And at a conference in June in Washington, Secretary Kerry was the host, and President Obama announced his intent to establish for this country, building on the National Marine Sanctuary Program and building on what President George W. Bush did in terms of establishing significant areas in the Western Pacific around the Northwest Hawaiian Islands and the remote Pacific Islands. At the time, the largest fully protected area, when George Bush did this, for anywhere in the world, where even the fish were safe. And now it is expanded by what President Obama is proposing, much larger than all the national parks in this country put together. And just as early in the 20th century, when national parks got started in the United States, some say the best idea America ever had, an idea that caught on around the world. Well, now, in a way, the United States was again a leader in the 70s, but other nations, like little tiny Palau, they're committing their entire exclusive economic zone to a plan for protection. Maybe we are now going to be following instead of, oh, we have some leadership, but maybe we have to think bigger than we have heretofore about what it's really going to take. So hope spots, it's a generic term for protected areas, marine sanctuaries, areas that if we protect them provide some measure of hope. The National Geographic Society has been promoting with Enrique Sala something called pristine seas. Let's find those areas like in Palau or in Kingman Reef, one of the areas that Obama is proposing to expand. Areas that are still in pretty good shape, I mean, really good shape. Don't let them degrade any further because they are reasons for hope. They're healthy. They're likely to have the elements of resilience that we need in the face of warming, in the face of pollution, in the face of acidification. And we need to give ourselves the best chance we can, sort of a hedge against the unknown and unexpected. We know, whatever we know, is that we need to exercise the precautionary principle, protect what we can, restore what we can, to give ourselves the best chance going forward.
It seems that the oceans are so resilient, and that even though when you take all the commercial fishing boats on the planet and put them together, and whatever that number is, it just, from the public's perception, it seems like there to be an inexhaustible supply, and maybe we can just.
So 50s.
So 50s, it is 50s.
Well, I think that's the movie that I was watching.
That's what we used to think.
But let's talk just for a minute about the Ross Sea and the Chilean sea bass.
Right.
I understand that these fish are not Chilean sea bass, but they're
Patagonian toothfish.
a toothfish that
Ice
takes
fish, yeah.
200 years to evolve.
Well, about 30 years, or well, decades to mature. And they may live to be a century old. And orange roughy, some have been aged to be perhaps as much as 200 years old. I mean, wouldn't you? They're our fellow vertebrates. Maybe we can learn something from them about becoming 200 years old, or instead of just eating them.
Well, maybe this is a good segue to go to a little bit of science from Susan, and I want to make sure we have enough time left to see some of Allison's wonderful photography from Alaska. So do we have the PowerPoints ready?
I really just have one slide, and Sylvia kind of talked about it before. It's this image of the planet with its water view and us draining off the water from the planet. And you see, of course, when you drain off that the Earth is not, underneath the ocean, is not flat. It's got lots of geological features, deep trenches, high mountains. And this is a ball with all of the water, and that is all of the fresh water, including that locked up in the polar ice caps. And that tiny one is all of the water that is available for us as humans in the form of available fresh water. And I put this up in part to illustrate just the point that you have been making, that most humans look at that first picture, that picture from space, and see just the huge magnitude of all of that blue and think how, wow, that's just indestructible. It cannot change. But in reality, it is a limited resource. And the ocean is a limited resource in terms of what it provides to us as services for humanity and for our life. I am a scientist. I'm a science junkie. I will fully admit to it. For me, the mystery of all of this is the interconnectedness of our planetary system. The ocean as a system itself, its physics, its chemistry, its biology, how it interacts with the atmosphere, another point of our planetary system, how it interacts with the land, the seafloor, ice, and of course, the biggest probably contributing forcing function right now, humanity. And knowing those interconnections in science is a challenge. It's a complex system. It is a very complex system. But we're in that age of really being able to look at those interconnections and begin to look at the surprises that come out of a complex system because of the ability to look at data, to bring different types of data together, to mine that data, to use our own visualization to see what properties or behaviors of that system can emerge that can tell us about what we're doing. And hopefully tackle some of the bigger scientific questions.
That's great animation.
Is that, oh, yeah.
That's perfect.
Well, I mean, a systems approach, now that's something that I think is becoming more and more in the vernacular of science, and looking at, the waste of one process and how that goes to become the fuel of another, and as Mother Earth and Mother Ocean and Mother Nature.
Grandmother Nature.
Grandmother Nature. Why do I think of an albatross? Have that capacity, and that the ocean perhaps is our biggest teacher of how that actually works. I mean, when I was studying marine biology, I remember that they said that 90% of all life on Earth existed within that, 1/2 mile along the coasts of all of the land mass.
That was before we began exploring the deep sea and realized that every drop of water in the ocean has life associated with it. We weren't counting the bacteria when that was, or a lot of the other creatures most of the new discoveries are actually down deep. The greater new discoveries occur the deeper you go. The Census of Marine Life 10-year study, they verified that with facts and figures that we have so far only named about 250,000 critters that live in the sea, not really counting the bacteria and other microbes that now outnumber everything else if you really get right down to it. But, the largest number of the remaining 1.25 million that have been named are mostly insects, beetles, all those creepy crawly things with 6 legs, 2 pairs of antennae and all that, that 500,000 are in that category alone. But what is in the ocean that we have yet to discover when we've only really effectively looked at about 5%, right?
That's about 5%. It's about
Yeah.
5%. And every time we go into the ocean, we can identify new things. 90% of the biomass in the ocean is microbial.
Yeah.
You cannot see it on those beautiful pictures that Sylvia showed. And so let me just tell you a story that illustrates where science can go on just one bacteria. Okay, and that's the Alexandrium bacteria. It's known for creating harmful algal blooms when it can bloom that is very toxic. It's toxic to fish, you have to close beaches, it can be harmful to humans. So, and it used to be that, if there was any sort of indication that there might be a harmful algal bloom in progress, things would be shut down. Fisheries would be shut down, beaches would be shut down, whole economies would suffer. Well, science has studied the Alexandrium bacterium and looked at its biological life cycle. They reside in the sediments of the seafloor for a long period of time. And biology figured out, well, what is that life cycle? What wakes it up? Okay, so that it begins to come out of the sediment and begin its life cycle. Science also has said, well, how does that bacterium interact with the physical environment that in the ocean, so that it transports its way up from the sediments into the surface waters? And as it's going, how is it feeding it? Where's the nutrient supplies that are coming from? Can I identify where there's nutrient? It's identified those. It has now tried to figure out how to model that life cycle, that biological life cycle, with integrate it with the physical life cycle. And oh, by the way, the winds have to come in too, because the winds provide the stress for the currents to move this bloom around and then create a warning system. Now, that's not all it did. It said, oh, let's now study the genomics. We now have all of this genomics and proteomics studies that the biomedical profession has used so much to advance our own human health, to study sort of this process and the differential parts of bacterium, Alexandrian bacterium. And lo and behold, we had closed a fishery for 25 years because we thought it was the same as this coastal harmful algal bloom that was over on Georges Bank instead. But through that genomics, we discovered that it entirely different, and it was not toxic. And after 25 years of a closure of a fishery and the development of a quick test to determine if it is going to be toxic, this opened up a fishery. So you've seen a whole cycle of understanding that complex biophysical interaction with the right data, with new tools that is able to now do a warning system, which is in, by the way, test operational basis with NOAA, and how that impacts the economy. It's a nice story. It's a nice story where all of our science works together.
It's a great story, and I think it gives us an illustration of how if we take our foot off the accelerator on old Mom Earth and all of her systems, how resilient and what tremendous healing powers are inherent there.
There's still some question about how deep is the deepest place in the ocean. You know, I've done 2 atlases of the ocean for the National Geographic. And that means that I coordinate a lot of data and try to find out answers to questions such as, how deep is the ocean? I mean, like, how high is the sky? We ought to know these things. But when I set about trying to get the number to put in the atlas, there were numbers ranging up and down and all over the place, because it's hard getting straight answers to straight questions like that when you're talking about how deep down is it 7 miles below the surface. When Don Walsh and Jacques Piccard tried to find that out when they took the Trieste there in 1960, what they did was take hand grenades, lob them over the side, and when they exploded, and they listened for the echo coming from the deep ocean, and the longer the echo, the deeper the ocean. And so they lobbed hand grenades here and there and everywhere until finally the longest, that's where they put the Trieste down. We're a little more sophisticated today than in 1960, but still, there are all these aberrations of cold water, warm water, different sensors. So anyway, but James Cameron came up with a definitive number so that now the National Geographic is revising all of its atlas. So we have a pretty good idea. And also the fact that there's life all the way down. I mean, that's surprising to some. People once thought that life could not possibly exist in the deep sea. It was too cold, too dark, all that pressure, no possible way that life could exist. And we can exist down there, but life in many forms does. And so I think the greatest excitement, what's coming out of the deep exploration from Woods Hole, what's coming out of China, they have a 7,000 meter submersible, plus deep robotic device in 1990s. One, Nereus, the deep diving robotic device that Woods Hole has, alas, was lost during exploration off New Zealand fairly recently. Really tragic loss. But here's the thing. How many airplanes are there? How many boats are there? Submarines are there? How many robots are there that can go into the deep sea? We have really been investing in what goes up in the sky, and hallelujah that we have, because we know a lot about the way the world works. And we can take ourselves all over the place on the planet because of that investment. But in the ocean, veer in terms of investing in appropriate technology. So talking with Charlie Rose earlier, just a few days ago, James Cameron spent about half his time talking about his dreams of wanting to be able to go into the ocean silently and to be able to, you know, being there robotically is great. We need all of these instruments. They can do things that humans can't do. But there's no substitute for taking ourselves. Cameron said famously in a Newsweek interview that we have to take ourselves, the personal experience. Little kids don't want to grow up to be robots. They want to be explorers. I mean, there's a human factor. I love exploring with all the tools, but I want a complete toolbox, including tools that enable any of you who want to go, who are poets and writers and dreamers and schemers, whatever. We need to go see this planet, experience it. National Geographic says a picture is worth 1,000 words, but they also say an experience 1,000 pictures. I mean, if you want to have a meaningful, if you want to make a deal with somebody, you can send pictures, you can Skype, but if you really want to get to the heart of it, it's a face-to-face encounter. If you want to know what a good wine tastes like, you don't look at a picture. You taste it, right? I mean, come on.
Well, I guess we're unfortunately out of time, and I think that's a great place to end. And I think we should just leave the audience with, let's taste it. So.